Okay, hello. So I'm here with the week 10 recorded lecture, which is going to replace the Thursday class that is going to be a review class instead. And to start out with, I found a really nice video. The title of the video is exactly the same title as today's class, What is an Integral? And this video is only 7 minutes long, and it has a really super great condensed summary of what we're doing. So the first 5 minutes are a super fast summary of what we're doing today, and the last 2 minutes are what we're going to actually do on Tuesday's class. So watch the video. It's a really good place to start. You're going to get all the main ideas, and then in the lecture we'll go over them in detail and do like some hands-on examples. So pause this video. I'll wait. Go watch that first, and then come back. Okay. So now you've seen the video and you're back. So what we're doing is integrals. We're starting integrals, and you might have heard that integrals are the opposite of derivatives, but actually this is kind of a miracle. I would refer to this thing as a miracle. The fact that derivatives and integrals are opposites, that is the miracle of calculus. The miracle of calculus. So I really think of the topics we've done in this course. First we did, really everything came from inequalities. Inequalities and logic. That was, oh, let me build it the other way. Let's build it the other way like a tree. Okay, here we go. You got inequalities, and logic. Those are like the bedrock that everything else is built off of. Then there was this trunk of the tree, which was the epsilon delta definition. And from the epsilon delta definition, we also got the limit laws, and we learned all about limits. And then we spent a lot of time in this branch of the tree on the derivative branch of the tree. And derivatives are this question of how things are changing. And it solves this important problem of the instantaneous rate of change is a nonsense thing until you think about it, because you're dividing by zero. How can something be changing in a single instant? And derivatives solve that problem, and you get all sorts of mileage for free coming out of derivatives. So derivatives are great, and they solve this issue of instantaneous rate of change, and they let you do all sorts of things. Totally separate to that, you can do something called integrals. That's what we're going to do today. Integrals. And integrals, just like derivatives have a problem of dividing by zero, integrals have a problem with adding up infinitely many things. So you want to figure out something like the area. That's what we're going to see. And figuring out the area involves adding up infinitely many small rectangles. How are you going to do that? And the answer is going to be a limit. So integrals are a special type of limit, and the limit is solved. The fact that we did limits solves this problem about integrals. And you can think about them as two totally separate branches. Derivatives are about instantaneous rates of change. Integrals are going to be about areas or like adding things up. And, for a long time, for hundreds of years, they really were separate. But this guy Newton came around and he discovered something which is like a miracle. And it's so miraculous, I'm going to use the special rainbow pen. And there is a bridge that connects integrals and derivatives. So they look like they're two separate branches. When we do the definition, they're going to be two separate things. But there is actually a secret rainbow bridge that connects them. And that secret rainbow bridge is called the fundamental theorem of calculus of, the rainbow bridge is nice, but it's not so readable. Let's try it in a different color. What do we do for rainbow bridge? Let's try this cool looking one. Okay, the fundamental theorem of calculus is the rainbow bridge calculus that connects integrals and derivatives. And so what we're doing in this class today, we are learning what an integral is. We're going up the branch from limit laws to integrals the old-fashioned way to learn what an integral is. And then once we know what an integral is, in next class we're going to do this bridge that connects derivatives and integrals. And you'll see that bridge is so useful that you sort of almost never think of an integral on its own after that. So after that, every time you want to calculate an integral, you turn it into a derivative using the fundamental theorem and do it that way. Okay, so that's a high-level overview of where we're going. But to start with, we got to learn what is an integral. The same way we learned what is a derivative. And this is something people coming out of high school often get mixed up. They confuse what is a thing with how to calculate the thing, right? A lot of people knew how to calculate limits without knowing what a limit is. A lot of people know how to calculate derivatives without knowing what a derivative is. So don't get mixed up on what an integral is. That's what we're doing today. And if you saw the video, the very short answer, the integral, what is an integral? The one-line answer. An integral is the limit. Answer. Question, what is an integral? Answer. It's a limit of a Riemann sum. Limit of a Riemann sum. That's the short answer. Okay, what is a Riemann sum? That's what this section is on. Approximating areas, Riemann sums. Suppose we wanted to find the area u blank under the graph of a straight line that lies above the x-axis and between 2 points x equals a and x equals b. So here's a little graph like that. We got some nice curve. We want to find the area between them. If it's a straight line, we can do it because we have formulas for finding the areas of basic shapes. So if it's a straight line, that's a trapezoid. You can look up the area formula for a trapezoid. It's some simple thing like a rectangle, no problem. But what about finding the area under the graph of a general curve y equals f of x and above the x-axis between 2 points, between x equals a and x equals b? So how do you find the area if it's a crazy curve where instead of being this nice thing between a and b, what if it's some crazy curvy curve? Then what do you do? So if it's not exactly a circle, you can't use the circle formula. You got to do something else. So this guy, Bernard Riemann, who is one of the most famous mathematicians of all time, he had this idea. Let's carve up the desired area into what? Into r blanks, into rectangles. Rectangles. And use the area to estimate the true area. So we can't get the true area directly. What we can do is we can estimate it using rectangles, and then we can hope to find a way to make our estimation more and more accurate. He called this the Riemann sum. Okay, so probably what actually happened is he invented this thing, and then somebody else was like, you and Riemann invented it, let's call it a Riemann sum. So here's how it goes. Choose a number n and divide up the interval ab into n pieces by choosing a list of points. So if you have some interval, let's for the sake of concreteness, let me scroll forward a bit and let me do 0 to 2 pi, and I'll do it with 4 pieces. So for example, if a equals 0 and b equals 2 pi and n equals 4, we're taking the interval 0 to 2 pi and we're dividing it up into 4 pieces. So there's going to be a middle line here at pi. There's going to be a pi over here at pi over 2. There's going to be a 3 pi over 2. So we've taken the interval, we've cut it into 4 pieces, and we're going to label the pieces. So we're going to call the first bit x0, then x1, and x2, x3, and x4. So x0 is 0, x1 is pi by 2, x2 is pi, x3 is 3 pi by 2, and x4 is 2 pi in this example. In general, you can do it with any division you want. So they don't even have to be uniform pieces. You just take an interval and cut it up however you want. The n pieces are sometimes called subintervals. Subintervals of AB. The kth subinterval is this one from x k to xk plus 1. So for example, when k equals 2, the second, the second subinterval, right? The second subinterval will be this one from pi over 2 to pi. Okay, and I realized if I'm going from pi over 2 to pi, that's the second subinterval, right? The first subinterval is from 0 to pi by 2. So the second subinterval, it should be going from xk minus 1 to xk. Okay. All right. So that's what we've done so far. So far, we've divided up the x-axis into pieces. For each subinterval, choose a special x value, star stands for special, x star k somewhere in the subinterval. So x star k is somewhere in between xk minus 1 to xk. So for example, in my example over here with 4 subintervals, so I had 0 to pi by 2 to pi to 3 pi by 2 to 2 pi. I have to choose a special point in each one. So you could, in principle, pick some zany thing like that, and you say this is x star 1, this is x star 2, this is x star 3, this is x star 4. You could do that. However, usually, for the sake of simplicity, and a lot of the examples we see will have this pattern, usually you pick the left or the right just to keep things simple. So you do this. Those are the points. So this will be x star 1, this will be x star 2, this is going to be x star 3, and this is x star 4. So in general, you can pick any point in the interval, but this special case is if you pick always the right point, that keeps things simple. So there's a lot of choices to be made in a Riemann sum. For each subinterval, draw a rectangle with a height of f of x star. So the height of the rectangle is the value of the function at the special point you chose in step 2. The base of that rectangle spans the entire subinterval xk to xk minus 1. So, for example, if you were doing this function and this image turned out a little weird. Let me just make up my own example. And in fact, let me use the example coming up because we're gonna do this one in detail anyway. So we might as well reuse it. So I'm gonna take this guy. I'm gonna put it up here. Okay. We're gonna use this example instead. And if you want, you can skip ahead in the notes to where this guy is being used, and you can just fill it in on that picture. So we said we're dividing this up into 4 pieces. So this was x0, x1 is here at pi by 2, x2 is here at pi, x3 is here at 3 pi by 2, and x4 is here at 2 pi. And then we picked the special x values, and I said let's do these right points. Now, that was step 1 and 2. Step 3 says, make the height of the rectangle the value of the function at the x value you chose. So these were the x1 star, this is x2 star, this is x3 star, and this is x4 star. So find the height of the rectangle will be the value of the function at that x value. So here are the heights of my rectangles. And look, this last one happens to be height 0. Height 0 is okay, that's allowed. The base of the rectangle is the entire subinterval. So the base of the first rectangle is this thing, first rectangle base. And that means the entire rectangle looks like this. It is height given by that height of the function, and then the base is everything to the left of that. Same thing with this. So we got these rectangles, and these are approximating. This last rectangle is height 0. It's got area 0. And the idea is this silly division by rectangles is supposed to approximate the area of the entire curve. So the total area, the area of the kth rectangle, what's the area of the kth rectangle? Area is base times height. The height of the function is the height of the rectangle. That's f of xk star, right? That was the height of the thing. The base spans this entire subinterval. So what is the base? It's the length of the subinterval, xk minus 1. That's the area for the kth rectangle. If you add them all up, you do a1 plus a2 all the way up. In our case, there's going to be 4 things. You add them up, and when you add them up, you can use this sum notation. So this sum notation is telling you add up all the values of the formula. So of the formula that appears here, add up all the values for all I values from 1 to n. So it is kind of like, if you know programming, it's like a for loop. We're looping over all the possible values that this I parameter could be, and we're adding up what's going on there. And okay, I guess in this case there's some things missing. The star is missing, and this should be xi, and this should be xi minus 1. So we're adding up all of these rectangles. We're adding up their areas. This crazy notation with the sum, it literally means exactly this. Add up the areas. That's all it means. Okay. This estimate, so right, adding up the areas doesn't give you the true value. The estimate of the area is called a Riemann sum. To simplify things, we often consider a simple special case. So in general, you can pick the points xi star anywhere, but the simple special case are the uniform Riemann sum. That's where the intervals are all equal. Uniform Riemann sum with n subintervals divides the interval into n equal pieces. So instead of having x1, x2, x3, all of the pieces are equally spaced. And when the pieces are equally spaced, you can talk about a delta x value. Delta x value is the total width of the interval, divided by the number of intervals. And the example we did was exactly one just like this. So the example we did over here, we had an equal spacing of the interval 2 pi into 4 equal pieces. In general, you could do something more complicated. You could do something like this. I don't know. You have lots of little pieces there, and then you have a big piece like that. But the uniform Riemann integral, or the uniform Riemann sum says make them all equal, and the spacing between them is delta x. In this case, delta x is pi by 2. Okay. That's delta x. The endpoints of the subinterval, because all the spaces are equal, there is a nice formula to get the location of the kth location. You start at the beginning, and you move over k times the length of the interval. The left or right Riemann sums specify where you should choose the point x star. They use the left Riemann sum uses the left endpoint, and the right Riemann sum uses the right endpoint. So when you do a left Riemann sum, the special point is on the left, and when you do a right Riemann sum, the special point is the point on the right. And we did the example, this example over here, this is a right uniform Riemann sum with n equals 4 divisions. So it's uniform because all the points are uniformly divided. It's a right Riemann sum because I chose the special star values to be on the right end of the interval. And in general, you can do lots of things, but already that is a really good start of possible things to do. And if you do that and you look at our formula, you get these special nice formulas. So the general formula is more complicated because delta x might change from term to term. But in these ones, delta x is always constant because it's a uniform division. And also, you don't have to worry about what x star is because x star is just equal to either xk or xk minus 1. And we're going to do an example right now to show you what this looks like. Use a right uniform Riemann sum with 2 subintervals to estimate the area below y equals 3x from 1 to 5. That's example 1. And I guess the computer goofed again and didn't give us any space to do it. But let's try to do it. So here's the function. Y equals 3x. Here's x equals 1, and here's x equals 5. And we want to use a Riemann sum. We want to divide this into rectangles to estimate the area. So because we're doing 2 subintervals, the only point in the middle is going to be x equals 3. So there's going to be one interval from 1 to 3, and the second interval from 3 to 5. The question tells me to do so that was a uniform Riemann sum with 2 subintervals. That's how I know there's two intervals, and so intervals are from 1 to 3 and 3 to 5. And so delta x equals the width of this interval is 2. It's a right. In the question, they told me do a right Riemann sum. So I'm going to pick the right endpoints at x equals 3 and x equals 5 as the heights of my rectangle. So the special points are x star 1 is 3 and x star 2 is 5. They're the right endpoints. And if you have all this, you can add it all up. You could also just directly use the formula. So the formula is going to be the sum from k equals 1 to 2 f of x. Okay, we're doing a right Riemann sum though, so it's this one, f of x k times delta x. Or because it's a sum of 2 things, you can just write it like this, f of x1 delta x plus f of x2 delta x. In our case, this is f of 3 times 2 plus f of 5 times 2. And you can see that directly the height of this left rectangle is f of 3, and the height of this taller rectangle is f of 5. And we're adding up the areas of the rectangles. This is the area of the left rectangle, and this is the area of the right rectangle. In our case, the function, we can evaluate it because it's the function 3x. So it's 3 times 3 times 2 plus 3 times 5 times 2. And so that is whatever that is. This is 18. That one is 30. So the answer, final answer, 48. The area that we got from our right Riemann sum was 48. So 48 is some kind of approximation for the area under this curve. Doesn't seem very useful yet, but it will be, I promise. Okay, here's another example. This is the example we started above. So we had Riemann sum. This time we're doing a left uniform Riemann sum. We have 4 subintervals. So what does it look like? There's 0, there's pi by 2, there's pi, there's 3 pi by 2, and there's 2 pi. And the width here is delta x is pi by 2. Pi by 2. Okay, we're doing a left Riemann sum. So the special points are taken on the left of the intervals. So it looks something like this. And we want to know the area under these rectangles. So this is the function. Y is sine of 1/2 x. You can write out the general formula for a left uniform Riemann sum. The sum from k equals 1 to n, adding up the area of n rectangles. What is the formula for the area of the nth rectangle? It's f of xk minus 1. This is the height of the rectangle times delta x. Delta x is the width of the rectangle. Okay, and so if you do that, in our case, it's a sum over 4 things. There's 4 terms. So there's going to be 4 terms. There's f of x0 times delta x plus f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x. And in our case, all the values are quite simple. x0 is 0, so f of 0. Delta x is always pi by 2. x1 is pi by 2, so f of pi by 2 times pi by 2. Maybe I'll draw the equal sign in a little bit more of a somewhere in the middle. F of x2 is pi times pi by 2. And f of x3, that's the third point, f of 3 pi by 2 times pi by 2. So I'm really writing down the formulas for the areas of these 4 rectangles. Rectangle 1, rectangle 2, rectangle 3, and rectangle 4. That corresponds to these 4 terms exactly. Those 4 terms exactly. Okay. So now I just got to plug in and do it. F of 0 is the sine of 0. So sine of 0 times pi by 2 plus the function we're doing is the sine of 1/2 x. So f of pi by 2 is sine of pi by 4 times pi by 2. The third term, f of pi, is sine of pi by 2 times pi by 2. And the fourth term is sine of 3 pi by 4 times pi by 2. Okay, and you can figure these out. These are all special angles. So sine of 0 is 0. 0 times pi by 2 is 0. The sine of pi by 4 is square root of 2 over 2. The sine of pi by 2 is 1. That's a thing of height 1. And you can see that visually. It's hitting at the top, right? We know that the third rectangle is height 1. Okay, 1 times pi by 2. The third one, 3 pi by 2, you're back down to square root of 2 over 2 pi by 2. And again, you can read that off the graph. It's the height of the rectangle. And if I did it correctly, the picture is supposed to be symmetric. So the height of rectangle 2 and rectangle 4 are supposed to be the same, even though they didn't come out quite that way in the picture that I drew. But they're both square root of 2 over 2. Okay, and you could add this up. I'm not going to bother simplifying it. This is perfectly fine. So that is the idea of a Riemann sum. A Riemann sum is adding up rectangles to estimate an area. Riemann sums, not so exciting. Limits of Riemann sums, this is where the magic happens. So we know the idea of a limit is the subtle idea And a Riemann sum is kind of this silly thing, like who the hell cares about these rectangles? But if you do the limit of the Riemann sum, even though every Riemann sum is wrong, the limit of the Riemann sum is right. So what happens as n increases and the rectangles get smaller? So here is a nice visualization with pictures of what was in that video from the beginning. The thinner you make the rectangles, the closer the estimate is. As the width of the rectangle decreases and you use more and more rectangles, the accuracy of our estimate increases. So what happens if we let the width of all the rectangles in the partition approach 0? It doesn't make sense to say let the rectangles have 0 width. Rectangles of 0 width make no sense. They have area 0. But you can do a limit. And so this is the beautiful thing. All of the hard work was baked into what we did with limits. The Riemann sums are always wrong, but you can do the limit of the Riemann sums. What does this look like? We're doing the limit as n goes to infinity. N is the number of terms, number of rectangles. And we're doing a sum, some kind of Riemann sum. So the formula for Riemann sum is something like this. xk star, xk minus 1. The Riemann sum. Even though every single Riemann sum is off by a little bit, as you take the limit as n goes to infinity, you converge, the whole limit will approach the actual value of the area underneath. So we should get the exact value, not the approximate value. It's always approximate if n is some finite number, but if you do the limit as n goes to infinity, you get the exact value. That is, our estimate becomes exact in the limit. Just like derivatives, which were also a kind of limit, we also have a compact notation for this limit. So every time you do an integral, it is secretly, under the hood, it is a limit. This is the same idea as when every time you did a derivative, it was secretly, under the hood, a limit. And it's exactly this problem with infinity and zeros. In derivatives, dividing by 0 doesn't make sense, so we use a limit to go around that, to sneak around. Doing the area under a curve doesn't make sense because you need infinitely thin rectangles. How do we get around that? We just approximate it with some number n, and then we do the limit as n goes to infinity. So that's what we're going to study in this section is integrals. Integrals are always a special type of limit. So the definition of this crazy symbols, when you see these crazy symbols, just like when you see a derivative, these symbols mean do the limit of something. And the limit of the thing we're doing is the limit of the Riemann sum. F of xk star, xk minus 1. As long as the limit exists, the limit is the definition of the definite integral. Definite integral of the function f of x between a and b. So this notation means it's defined to be equal to this limit, and you read it out loud as the definite, as this phrase, the definite integral of f between a and b. We write it down with this notation. When this happens, when the integral exists, if the integral exists, then we say the function is integrable. Just like with derivatives, if the derivative, that was a limit, if that exists, we say the function is differentiable. For integrals, we say it is integrable. AB is called the domain of integration. And here's a fact: all continuous functions are integrable. So for derivatives, there were corners and things. Not every continuous function was differentiable, but every continuous function is for sure integrable. This is a hardish theorem to prove, but we're just going to take it as a fact in this class. So the limit always exists for continuous functions. That's very nice. I want to take a second and point out this notation. You might think this notation is completely nuts. Who invented this S symbol, and where is it coming from? Just like the Leibniz notation, dy dx is supposed to remind you of the limit of the change in y divided by the change in x. This was the Leibniz notation for a limit. This definition of a limit, or this notation for a limit, has the same kind of thing. This dx over here is supposed to remind you of the delta x, and this funny squiggly curve is supposed to remind you of a sum. So it is kind of like a sum. This blue part is kind of like a sum of what are we summing up? We're summing up the value of the function times the width of each rectangle. So that's how the notation was invented, and it's not perfect, but that's where it's coming from. The same way dy dx is supposed to remind you of doing a division, the integral symbols are supposed to remind you of a Riemann sum. Okay, so we've done Riemann sums. We've done the limit of Riemann sums. That's the definition of the integral. And when this limit exists, we call it integrable. Okay, so here's the thing sometimes people get confused by. If f is integrable and a and b are numbers, the definite integral always gives a numerical result. So the integral from a to b of f of x dx, that's a number which is equal to some limit of something. You can also think about it as an area. Thus, the variable we use in integration is not important. So it looks like there's an x here, right? F of x dx. But the actual thing that we're getting is not a function of x, it's a number. So the x is what we call a dummy variable. It's a dummy variable because the final answer does not depend on x. So if somebody says the integral from a to b of f of x dx, that's exactly the same thing as saying the integral from a to b of f of t dt. They both represent the same limit. So they represent the same exact thing. You could put any symbol you want there. So you could put a spade symbol in. You could put in a heart. Yeah, let's do it. Let's do a nice heart. So the symbol in here doesn't matter. Later on, we're going to learn that, something about functions. So don't get confused. This thing is a number, not a function. By its definition, the way we defined it, the integral is the area above the x-axis and below f. So as long as you draw a function above the x-axis, then our limit that we wrote down is exactly the area from this Riemann sum thing. And this works as long as the function is positive. As long as the function is positive. Everything we did, we were assuming that the height of the rectangle was a positive number because it's above the x-axis. So we used f of x. If f is negative, then something different is going to happen. So more generally, for any f, this definite integral represents the area above the x-axis and below f for intervals where f is positive, minus the area below the x-axis and above f when f is negative. This is sometimes called the net area. I think the easiest way to understand this net area thing is to do an example. Use the area of triangles to evaluate the integral from -1 to 2 of 3x dx. So the function 3x dx looks like this. That's the function 3x. And we want to do the integral from -1 to 2. The integral is equal to the net area. This is the formula we're going to use to do this problem. What is the net area? Based on the description up here, the net area is the area above the x-axis minus the area above x-axis minus the area below the x-axis. Okay, in this case, it's the area of this triangle. Let's do it in a different color. Let's do it. It's the area of the green triangle minus the area of the yellow triangle. So area of green triangle minus the area of the yellow triangle. And this really comes from the definition of the limit. In the limit, we took the value of f. So in the definition of the integral, we took the value of f. And if f is negative, you're not doing area, you're doing negative area. That is why you get this net area formula. So what is it in this case? What's the area of the green triangle? Well, the green triangle has width 2. And what is its height? Well, this is the function 3x, so its height is 6. So 2 times 6 divided by 2, that's the area of the green triangle. What's the area of the yellow triangle? Well, its width is 1, -1 to 0. And its height here is 3, right? That x equals -1. So the area of the yellow triangle is 1 times 3 divided by 2. And so if you add this up, you get 6 minus 3/2. That's the integral. And the point is the integral is not quite area, it's this net area. You have to make sure to subtract off the parts where it's negative. Okay. Properties of the definite integral. So based on what we have this new thing, the integral, that does area. It has some nice properties, and we're going to use the properties. So given our definition, we can determine a few important and mostly intuitive properties of the integral. And here are the examples. There's basically a list of them. These are like the limit laws or the derivative laws. These are the laws for how integrals should behave. So the first one says, what happens when you integrate a constant? So if you have some height value k, and you look at the function that is always k, and you look at it between x equals a and x equals b, what is the height of this? What is the area underneath this function? And the area is this rectangle. The height of the rectangle is k, and the width of the rectangle is b minus a. So the integral is equal to b minus a times k. So the integral of a constant is the area of a rectangle. Very simple formula. Here's another one. Here's another fact. If you do the integral from a to a, so if the top and the bottom are both equal, what you're talking about is the area from x equals a to x equals a. And this is an area with no width. So this should definitely be 0. This should definitely be 0. Okay, here's another funny one. If you do the integral from x equals a to x equals b, so you go from x equals a, and you want to go to x equals b, and you want to find the area underneath. Funny thing that happens, this is equal to negative of doing the integral from b to a of f of x dx. And this seems really counterintuitive. So this one really represents the area from a to b. So going with a delta x value of b minus a over n for each of the rectangles, all of these rectangles, this dx really represents the width of the rectangle. In this one, I have one of these backwards. I really meant to write a to b. So the point is, when you go from b to a and you go from a to b, they're related by doing a minus sign. So what did I? Okay, I drew the picture wrong. Let me draw the picture as going from x equals b to x equals a. So in this one, if you have honest rectangles, their width is dx. But in this one, when you're going from a to b, you're going backwards. So on this side of the equation, you're going backwards, and because of that, your dx value is not the width of a rectangle. Your dx value is negative the width of the rectangle. And that is why you have a minus sign. So you can trace this back to the definition of the limit, and in that limit there's a minus sign when delta x is negative. And so this formula is true because of that. You could also just treat this as a notational thing. If you switch the top and the bottom of the limit, you have to put in a minus sign. Either way, it's a fact about integrals that you have to know. Maybe I'll delete some of these crazy annotations here and just leave the final fact. When you do the integral from b to a, that's negative the integral from a to b. Okay, here's another one. What if you have 3 points now? Suppose you have the point x equals a, you got x equals b, and you got x equals c. So the fact is, if you want to integrate all the area from a to c, you could first do everything from a to b, and then add it to everything from b to c. So integrals, they add up in the way you would expect areas to add up. Here's another one. If you have two functions, maybe you have one function f of x, and you have another function g of x. G has to be bigger g of x. And if f is less than g, then you can expect that the area underneath f, how does the area underneath f, how does that compare to the area underneath g? The area under g has to be bigger. So integrals respect inequalities. So the area under g is definitely bigger than the area under f. Okay, here's another one. What happens if you multiply a function by a constant? So you take a function, here's the function f, and you blow it up by multiplying it by some fixed constant. So everywhere you draw it, it's twice as big. This is the function k times f of x. It's the function f blown up. And hopefully you can see that if you blow up a function, then all the areas are also blown up by the same factor. So if you do the integral of k times the function, that's the same as doing k times the integral of the function. And again, this is an easy one to check with limits. Both these things are limits. This is going to follow by the constant multiple rule limit law. That's another way you can prove this from the limit definition, or you can see it with the picture. Lastly, you can do the difference of integrals. That's going to be the difference of functions, and then integrate it is the difference of the integrals. Again, it follows by the limit laws, the subtraction limit law, or you can see it visually. If you do f of x and g of x, I guess I want it the other way around. F of x and g of x, and you want to know the difference of the areas. So what is the green area is the total area under f. The blue area is the total area under g. And if you subtract those, that's the same thing as doing the yellow area, which is the area between f and g. That's another way of seeing this fact. But these are the basic facts about limits. Oh, I guess, okay, same thing with a plus. You can do it with a plus. Let me draw the picture for that. I guess the picture for, I'm going to leave the picture for this one for you to try. So the picture is a little harder because you got to draw the sum of functions. But all of these things are intuitive from the point of view of areas. All of them from the point of view of limits follow from the limit laws. These are just basic facts about integrals. And so coming up, we're going to do more stuff with integrals. There's one more definition on this chapter, which is the average value of a function. So the integral tells you the area under the function. The average value of the function is defined to be the area divided by the width of the interval. So if you think of area is width times height, the integral sort of adds up all the possible heights of the function f, and then you're dividing by the width again to get back to the average value. So this is the definition of the average value. Here's one example to do. Draw the following functions on the given axis. There's f of x equals 20 between -2 and 7, and there's f of x equals x between 0 and 3. So here's f of x equals x between 0 and 3. And f of x equals 20. This function is just always 20. It's always 20. Between -2 and 7. Okay. Use the formula for the area of a triangle and a rectangle to determine the average value of these two functions. So we're not doing just the integral, we're doing the average value. And to find the average value, you first do the integral, and then you just have to do a division at the end. So what is the integral? What is the integral of f of x from 0 to 3? The integral is the area, and it's the area of a triangle. So this triangle has base 3 and height 3. It's the function y equals x. So 3 times 3 divided by 2, that's 9 halves. The area is 9 halves. So what is the average value? The average value. The average value, by the definition, is you take the area and you divide it by 3. So in this case, it's 1/3 times 9 halves, also known as 3 halves. And this matches perfectly your intuition. So this is a triangle. The function starts at 0. It goes up to y equals 3. We found out that the average value was 3 halves. And that's exactly halfway. That's exactly halfway. So it makes sense that the average value of this like straight line segment is going to be halfway between the lowest and highest value. So average values of a function is a thing that sort of adds up all the possible values of the function and tells you what it is on average. You can do the same thing over here. Before we even do the math, we're going to do the math in a second to figure out what it is. What do you think the average value of something that is always 20? If the value of the function is always 20, what is the average value going to be? I think the average of something that is always 20, I'm really hoping the average value should also be 20. Let's see if it works with math. So the average value is 1 over 7 minus minus 2, right? Because that's what the formula says to do. 1 over b minus a times the integral. We do the integral from minus 2 to 7 of 20 dx. The integral of 20 from minus 2 to 7 is one of the rules. It's the area of this rectangle. So it's 1 over 7 minus minus 2 is 1 over 9. And what is the area of this rectangle? It's 20 because it's 20 high. How long is it? It's 9 wide. So the integral is 20 times 9. When we do the average value, we do a 1 over 9, and they exactly cancel out. The average value for this function is 20. Okay. So that is it for integrals. For what is an integral? The real honest truth is that an integral is the limit of a Riemann sum, and doing it that way, finding out the limit, is a real hard thing to do. So instead of like in the derivative section, we did a couple derivatives by hand using limits. If you want to do that for a Riemann sum, it really is a lot of work. So what we're going to do in the next section, we are going to skip doing these limits by hand, and we are going to learn about the secret rainbow bridge that lets you learn about what is the value of an integral using derivatives. And that secret rainbow bridge is called the fundamental theorem of calculus. Okay, so we'll see you next class when we do that.